Hi everyone, this is Mehdi Soleimanifar, a graduate student at MIT. I'll talk about the joint work with Aram Harrow and Saeed Mehraban, which is mostly about the partition function of quantum many-body systems. So let me begin with telling you about the setup. A topic that both in physics and computer science is studied is the spin systems, where you have n spins arranged on a lattice at a fixed temperature that we usually work with its inverse, denoted by beta. These spins interact with each other, and their interactions are described by a local Hamiltonian H, which is the sum of terms Hi, each acting on a spatially local region. So in computer science language, these local Hamiltonians describe constraint satisfaction problems, but I'll keep using the physics terminology in this talk. The focus of this talk is on quantum spin systems, but before getting to that, let me first tell you about the classical spin systems, where we assign a spin, which is a plus minus one variable, to each side or vertex of the lattice. The Hamiltonian of a specific spin configuration can, for instance, be something like this. If you let these spins interact with each other at a fixed temperature, they achieve an equilibrium state. And then there's a probability distribution that describes this state known as the Gibbs distribution. The normalization constant in this distribution is called the partition function of the system, which is the sum of these exponential factors. The partition function is not merely a normalization factor. It also encodes many statistical properties of the system, like the free energy or entropy. And it also shows up in computer science because it can encode interesting combinatorial problems. So in general, it's desirable to have algorithms for evaluating this quantity. And one subject of this talk is to achieve this for quantum spin systems. Before introducing these quantum spin systems, I think it's easier to first express the classical spin system, which is with a slightly different notation. So instead of a plus minus one variable at each site, each spin is now a matrix with plus minus one on its diagonal. The Hamiltonian is now a Hermitian operator, which is the sum of the tensor product of these matrices. And we often drop this tensor product for ease of notation. Similarly, we can represent the Gibbs distribution using an operator known as the density matrix. And the partition function looks something like this in this notation. So all we did was to put the variables on the diagonal entries of a matrix. In quantum spin systems, we can go beyond this and consider non-diagonal matrices. Now, instead of one, we assign three matrices to each site. And an example of a quantum Hamiltonian in this case is something like this. And the Gibbs state and the partition function are defined as before based on the Hamiltonian operator. We can consider other more general Hamiltonians that may involve more spins in each term. And when we say quantum spin systems, we refer to this setup. These Hamiltonians are used to describe quantum many-body systems. They appear in condensed matter physics, quantum chemistry, and quantum computing. And they exhibit many novel phenomena compared to their classical counterparts. So we would like to study their properties, and therefore we would like to estimate their partition function. It is known that evaluating the partition function exactly is sharply hard. Hence, our goal is to have an algorithm that, given the description of the Hamiltonian, outputs an epsilon additive error approximation to the log of the partition function, or if you like, an epsilon multiplicative approximation to the partition function itself. Then a natural question is how hard it is to find such approximation algorithms. It turns out the hardness depends on the temperature at which you want to estimate the partition function. This is a widely studied problem classically, so let me first tell you about that. It's actually not hard to see this temperature dependence of the computational hardness in two extreme cases. At very high temperatures, the Gibbs distribution is basically the uniform distribution, and finding the partition function is trivial. It's just the dimension of the system. At very low temperatures, the problem basically reduces to max CSP, so it's NP hard to evaluate things like the free energy. So as we see, the hardness changes from being trivial to NP hard as we vary the temperature. But in physics, we know about another phenomenon that occurs as we change the temperature, which is the transition in the phase of the system, where at some critical inverse temperature, say beta C, the properties of the system abruptly change, and the system enters a new phase. For instance, it can go from an ordered to a disordered phase, where in the disordered phase, the correlations between distant spins decay exponentially, while we may have long-range correlations or order in the ordered phase. This is one way to distinguish these phases. There is also a different method based on the complex zeros of the partition function that I'll describe in details later. It turns out that the physical phase transition is closely related to the hardness of approximation. And there are various results in this direction, some using the correlation decay and some based on the complex zeros. For instance, it's been shown that mixing in time is equivalent to mixing in a space, where mixing in time means that there is an efficient sampling algorithm with fast mixing time. And this is equivalent to having mixing in a space, which means that the correlations in the system decay exponentially. Using decay of correlation, we can also directly find deterministic algorithms for some systems. And on the other hand, it's been shown for systems like icing or hardcore model that is NP hard in the worst case to estimate the partition function beyond the phase transition point. Okay, these are based on the decay of correlations. But recently, Barvinok has introduced a new method for deterministically obtaining the partition function, which instead of using the correlation decay, it uses the characterization of phase transition based on the complex zeros of the partition function. And I focus on this method in a bit, but before that, let me talk about quantum space systems. So how does this picture change in that case? In the quantum systems, we still don't have a complete picture of how things are, but let me mention some of the things about classical systems that we know they carry over to quantum. In the two extreme cases, we still have the same situation. It's trivial to estimate things in the infinite temperature case, and at low temperatures, the problem is QMA hard, where QMA is the quantum analog of NP. We also again have the physical phase transition, which can be characterized by either looking at the decay of correlations or the complex zeros of the partition function. Again, there are some results connecting correlation decay to algorithms. In particular, Brandao and Castoriano have shown one direction of the equivalence between mixing time and space for quantum Hamiltonians with mutually commuting terms. They have also shown this for a general Hamiltonian, if besides a variant of the decay of correlation, they also assume the Markov property holds. There is a class of quantum Hamiltonians known as the sign-free or stochastic Hamiltonian, whose partition function can be directly mapped to that of a classical spin model. And then we can apply the existing sampling algorithms for that classical system to find the partition function of these quantum systems. And as I mentioned earlier, there is a new family of algorithms due to Barvinok that uses the complex zeros instead of the decay of correlation. In our work, we show that this method can be naturally extended to the quantum settings too. So before going into the details, let me first give you a brief overview of our results. We have some results that connect finding an approximation algorithm to the complex zeros of the partition function. And we have some results that connect the two different ways of characterizing the thermal phase transition. Let me begin by telling you more about these complex zeros and our first result. So to see why complex zeros of the partition function are connected to the thermal phase transition, let's look at the complex beta plane, where remember that beta is the inverse temperature. If we restrict ourselves to the real beta axis, the partition function is strictly positive. And things like the log of the partition function are analytic functions. And it doesn't seem like any of the properties of the system can abruptly change or have singularities. But this changes if we consider complex betas. Now, these exponential factors can pick up a phase such that when you add them together, these phases cancel each other and the partition function becomes zero in certain locations. As we change the number of spins in the system, the number and location of these zeros change. And in particular, in the limit of the number of particles or spins going to infinity, some of these zeros approach and accumulate around a specific point on the real axis. So the partition function at this point vanishes, and its log or the free energy become non-analytic, and hence a phase transition occurs. The study of these zeros was initiated by Li and Yan in a slightly different context, and it was later extended to thermal phase transition by Fisher. Hence, these complex zeros in the beta plane are often called the Fisher zeros. Now let me tell you about our first result, which is the following. There is a quasi-polynomial time approximation algorithm for estimating the partition function that works in the zero-free region, which is the inverse temperatures before the critical point where the zeros cross the real axis. The idea of the algorithm is the following. We start from beta equals 0, meaning at infinite temperature, and extrapolate the solution there, which is easy to find, to estimate the partition function at some other beta, which is constantly far from the critical point. As long as the endpoint is before the critical point, where these zeros accumulate and block the way, we can find a region of constant width and length that encloses both our starting and the endpoint, such that the partition function is not zero inside it, and all its zeros have some constant distance to this region. Therefore, the log of the partition function is analytic inside this region. And it turns out for quantum systems, we also need to assume that not only the partition function is non-zero inside this region, it is also at least some exponentially small value, so that its log is upper bounded by order n. I'll later show how we can get such a bound. So since the log is analytic inside this region, its Taylor expansion around beta equals 0 converges. Our algorithm computes the first k terms in the expansion, meaning basically the first order k derivatives. And that's our estimate for the partition function. But we know from Taylor's theorem that the error in this approximation is exponentially small in the number of terms. And if we want this, for instance, to be inverse polynomial, it suffices to choose k to be order log n. But how do we actually compute these derivatives? I don't get into the details, but it turns out that it suffices to, instead of finding the derivatives of the partition function itself, we instead find the derivative of, instead of finding the derivatives of the log of the partition function, it suffices to find the derivatives of the partition function. And it's not hard to see that the kth derivative of the partition function at beta equals 0 is proportional to the trace of h to the k, where h is the Hamiltonian operator. But h is sum of order n many local terms, and hence h to the k is also sum of n to the order k local terms. The trace of these local terms h prime I can be found in polynomial time. Therefore, the derivatives can be estimated in time n to the order log n, which is quasi-polynomial. Recent work after our result shows that this running time can be actually improved to polynomial time at high enough temperatures where we can use cluster expansions. All right, so that's our first result. In general, it's a hard problem to determine where the zero free region ends. And unless we pick a specific family of, say, translationally invariant Hamiltonians, exactly finding the critical point is hard. So in our second result, we give a general lower bound on the value of the critical point. In particular, we show that the partition function doesn't have any complex zeros inside a disk of radius beta naught, where this beta naught depends on the geometric properties of the Hamiltonian, like the degree of the interaction graph. The proof of this is based on a recursive argument that uses cluster expansions designed for quantum Hamiltonian. And the idea is to compare the partition function of a subset of the spins before and after adding a new spin to it. We show that inside that disk of radius beta naught, the partition function after adding the new spin is lower bounded by the previous partition function times a constant. And by repeating this argument multiple times, we see that the partition function of the whole system is lower bounded by an exponentially small value times the partition function of a single spin, which itself is just a constant. Therefore, the log of the partition function is at most order n, and this is what we needed in the extrapolation algorithm in the previous slides. But how do we prove this lower bound? As I mentioned, we use cluster expansions, which allows us to write the operator e to the minus beta h as a sum of the product of local operators hi. By taking the trace of both sides, this means we can write the partition function of the larger system as that of the smaller system plus some corrections that we can show they're actually small. Right. So far, we've only considered the complex zeros. But in our next result, we look at the connection between the zeros and the decay of correlations in the Gibbs state. As I said before, for temperatures above the phase transition point, the correlations between observables A and B, which is measured using this covariance form on the left-hand side, decays exponentially with their distance. The connection between this notion of phase transition and the zeros that I discussed before have been studied for translationally invariant classical systems by Dobberstein and Schlossman, who showed that these two notions are indeed equivalent to each other. In our work, we consider the quantum version of this question. And we show that for real temperatures, where there are no complex zeros around them, the correlations in the Gibbs state decay exponentially. This is when the distance between the observables A and B is at least logarithmic in the number of particles, or we can improve this to when the distance is just a constant if the Hamiltonian consists of mutually commuting terms, which is still different from being classical. Or when we have a general Hamiltonian, but it's on a 1D chain. So the condition on the absence of zero we use is more restrict than the one we use in our algorithm because we need to include various boundary conditions, but I'll ignore that here. The proof of this theorem is somewhat similar to the extrapolation idea I explained for our algorithm. We first define a function that measures the correlation between the observables A and B at a given inverse temperature beta. So this function is slightly different from that covariance form we had in the earlier slides, and is tuned to have specific properties. But it is the case that when this function is small, the correlations defined using the covariance is also small. In particular, we show that this function at beta equals 0, meaning at infinite temperature, is 0. So this makes sense since the Gibbs distribution at infinite temperature is just the uniform distribution, and the spins are not correlated. But not only that, we also show that the first m derivatives of this function are also 0, where m scales with the distance between the observables. In other words, this function looks very flat close to the origin. Then we show that in the range of inverse temperatures where the partition function is analytic, this function is also analytic. And we can use complex analysis tools to show that if the function looks very flat in the origin and it's also analytic, it cannot grow that much by going to a constant real beta. So the value of the function is small. And since this function measures the correlation between observables A and B, this means that those correlations are also small. And in fact, it turns out they are exponentially small. All right, this covers most of our results. I don't have time to go into the details, but we also applied Barbinuk's approach to other parameters of the Hamiltonian rather than the inverse temperature. In particular, we consider extrapolating in the external field, meaning at a fixed temperature, the spins not only interact with each other, but their energy is also affected by the strength of an external magnetic field. So the easy regime is when the field is very strong and all the spins align themselves along the field. And the hard regime is when the field is small and the interactions between the spins dominate. An example of such Hamiltonian is the ferromagnetic Heisenberg model that has this expression. So the XX, YY, and ZZ terms describe the interaction between neighboring spins, and the Z term corresponds to the effect of the external field. We denote the strength of the external field by mu, and similar to what we did before, we now look at the complex mu plane. And our goal is to extrapolate the solution at large mu to small but a constant value of mu. So to ensure this convergence of the Taylor expansion, we need to know the location of the complex zeros in this plane. And these are known as the Lee Yang zeros. So this can be obtained by mapping this system to a classical spin model and analyzing the zeros of that model, which is done by Suzuki and Fisher. So this way we can get a quasi-polynomial time algorithm at any temperature. So previously, by a result of Bravi and Gossett, a polynomial time algorithm was known for Hamiltonians that don't have the ZZ term. And this is again done by reducing this problem to a classical problem on counting the number of perfect matching. And then there are sampling algorithms for that classical problem by Jerome and St. Clair that can be used to find the answer. All right, here is a list of open questions. It would be interesting to find stronger results regarding the connection between the complex zeros and the correlation decay. The Barbinuk's method is fairly flexible, so perhaps there are more applications for it in quantum computing. You can also look at our paper for more details and discussion. So here are the references. And thank you for your attention.